Welcome to Echo 204, Study Session 9, Multivariate Differential Calculus. Introduction. When a function has more than one variable, there are two types of differentiation that can be considered: partial and total. The total derivative allows all variables to change simultaneously, while partial derivative allows only one variable to change, holding others constant. Partial derivative assumes that the variables of the function are independent of one another, and so other variables are treated as constant when considering a particular variable. Y equals f of u, f of v. The partial derivatives are given by dy by du. E.g., y equals 3u squared minus 3v. dy by du equals 6u. dy by dv equals minus 3. Observe the difference in notation compared with what we have had in single variable functions. Single variable functions, y equals f of u. Multivariate function, y equals f of u, f of v. dy by du or f prime of u. dy by du or f u dy by du. D square y by du squared or f prime prime of u. D square y by du squared or f uv. D squared y by dv squared. Example. Find all the partial derivative of the function y equals u plus 2v plus w squared, all in bracket, raised to power 2. Solution. To find dy by du equals fu, treat 2v plus w squared as a constant. Y equals u plus c, all in bracket, raised to power 2. dy by du equals 2 of u plus c in bracket. dy by du equals 2, then open the bracket, u plus v plus w squared, close the bracket. For dy by dv, treat u plus w squared as a constant. Y equals 2v plus c in bracket to power 2. dy by dv equals 2 of 2v plus c in bracket times 2. dy by dv equals 4 times, open the bracket, 2v plus u plus w squared, and close the bracket. Lastly, for dy by dw, treat u plus 2v as a constant. Y equals c plus w squared. dy by dw equals 2. Then open the bracket, c plus w squared, close the bracket, times 2w, which equals 4w, open the bracket, u plus 2v plus w squared, close the bracket. Example. Find fx and fy if f of x, f of y equals minus 10x y to power 3. Solution. Find f of x. Y must be assumed to be a constant. This function can then be mentally rearranged as f of x of y, which equals minus 10 y to the power 3 all in bracket times x, where minus 10 y to the power 3 is the constant coefficient of x. Therefore, fx equals minus 10 y cubed. For fy, the function can be assumed as having the form f of x, f of y equals minus 10x in bracket times y cubed, where minus 10x is a constant coefficient of y to the power 3. Therefore, fy equals 3. Then open the bracket, minus 10x in bracket times y squared. F of y equals minus 30xy squared. Second order partial derivative. 1. Pure second order partial derivative. And 2. Cross mixed partial derivative. Example 1. Given that a firm's costs are related to output of two goods x and y in the form TC equals x squared minus 0.5 xy plus 2y squared as equation 1, it is possible to find the first order partial derivative fx and fy, which translate to the additional cost of a slight increment in x and y respectively. Fx equals 2x minus 0.5y, equation 2. Fy equals 0.5y plus 4y, equation 3. It is possible to find three different second order derivatives partially, that is fm, fyy, that is pure second order partial derivative, then fxy equals fyx, cross partial derivative. Note, the cross partial fxy is always equal to fyx. This proportion is known as the Young's theorem. To obtain fm, differentiate equation 2 with respect to x, fm equals 2. For fyy, differentiate equation 3 with respect to y, fyy equals 4. Lastly, for fxy, differentiate equation 2 with respect to y, fxy equals minus 0.5. The same result is obtained if we differentiate equation 3 with respect to x. Optimization of multivariate function in economics. Many producers or sellers deal in more than one product item, and in order to maximize profit or minimize costs, they need an optimal mix of the products in which they deal. Optimization of multivariate function helps to achieve this. Conditions for optimality. Condition 1, first order, maxima. Fx equals 0, Fy equals 0. Minima. Fx equals 0, Fy equals 0. Second order, Fxs less than 0, Fyy less than 0. Minima. Fxs greater than 0, Fyy greater than 0. Third order, Fm times Fyy greater than Fxy in bracket to power 2. Minima, Fxs times Fyy greater than Fxy all to power 2. Example, a firm producing two goods X and Y has the profit function pi equals 64x minus 2x squared plus 4xy minus 4 y to power 2 plus 32y minus 14 to find the profit maximizing level of output for each of the two goods and test to be sure that profits are maximized. 1. Take the first order partial derivative, set them equal to 0, and solve for x and y simultaneously. Pi x equals 64 minus 4x plus 4y equals 0. Pi y equals 4x minus 8y plus 32 equals 0. Minus 4x plus 4y equals minus 64. Equation 1. 4x minus 8y equals minus 32 as equation 2. Add equations 1 and 2. Minus 4y equals minus 96. Y equals minus 96 divided by minus 4, which equals 24. To get x, 4x minus 8 of 24 equals minus 32. 4x minus 192 equals minus 32. 4x equals minus 32 plus 192. 4x equals 160. X equals 40. Take the second order direct partial derivative and make sure both are negative as required for a relative maximum. Pi x equals minus 4 less than 0. Pi y equals minus 8 less than 0. 3. Take the cross partial to make sure that pi xs times pi yy is greater than pi xy in bracket all to power 2. That is, minus 4 times minus 8 is greater than 4 to power 2. 32 greater than 16. We have now confirmed that the profit is indeed maximum. We can also find the profit at that point. Pi equals 64x minus 2x squared plus 4xy minus 4y squared equals 64 times 40 minus 2 times 40 to power 2 plus 4 times 40 times 24 minus 4 times 24 to power 2 plus 32 times 24 minus 14, which equals 2,560 minus 3,200 plus 3,840 minus 2,304 plus 768 minus 14. Pi equals 1,640. Example 2. In monopolistic competition, producers must determine the price that will maximize their profit. Assume that a producer offers 2 different brands of a product for which the demand functions are Q1 equals 14 minus 0.25 P1, Q2 equals 24 minus 0.5 P2, and the joint cost function is TC equals Q1 squared plus 5Q1 times Q2 plus Q2 squared. Find the profit maximizing level of output, the price that should be charged for each brand, and the maximum profit. Solution. First, establish the profit function in terms of Q1 and Q2. Since pi equals TR minus TC, we need to find the first TR. TR equals P1 times Q1 plus P2 times Q2. Make P1 and P2 the subject in the demand functions. P1 equals 56 minus 4Q1. P2 equals 48 minus 2q2. TR therefore equals 56 minus 4q1 all in bracket times q1 plus 48 minus 2q2 in bracket times q2. TR equals 56q1 minus 4q1 squared plus 48q2 minus 2q2 squared. Pi equals 56q1 minus 4q1 squared plus 48q2 minus 2q2 squared minus q1 squared minus 5q1 times q2 minus q2 squared. Pi equals 56q1 minus 5q1 squared plus 48q2 minus 3q2 squared minus 5q1 times q2. We can now maximize the profit function. d pi by dq1 equals 56 minus 10 q1 minus 5q2. d pi by dq2 equals 48 minus 6q2 minus 5q1. 10q1 plus 5q2 minus 56 equals 0. 5q1 plus 6q2 minus 48 equals 0 as equation 2. Multiply equation 2 by 2 to eliminate equation 1. 10q1 plus 12q2 minus 96 equals 0. That gives us equation 3. Subtract equation 1 from 3. 7q2 minus 40 equals 0. 7q2 equals 40. q2 equals 5.7. Substitute q2 equals 5.7 into equation 1 or 2. 10q1 plus 5q2 minus 56 equals 0. 10q1 plus 5 times 5.7 minus 56 equals 0. 10q1 plus 28.5 minus 56 equals 0. 10q1 equals 27.5. q1 equals 2.75. Take the second derivative to be sure profit is maximized. Pi qq equals minus 10 less than 0. Therefore, pi qq will be less than pi qq all raised to power 2. To find the profit maximizing price, P1 equals 56 minus 4Q1, which equals 56 minus 4 times 5.7. P1 equals 45. P2 equals 48 minus 2Q2, which equals 48 minus 2 times 5.7. And P2 equals 36.6. Lastly, the maximum profit. Pi equals 56Q1 minus 5Q1 to power 2 plus 48Q2 minus 3Q2 to power 2 minus 5Q1 times Q2, which equals 56 times 2.75 minus 5 times 2.75 to power 2 plus 48 times 5.7 minus 3 times 5.7 to power 2 minus 5 times 2.75 times 5.7. Pi equals 213.94. Exercise. Number 1. Given the profit function pi equals 160x minus 3x squared minus 2xy minus 2y squared plus 120y minus 18 for a firm producing two goods, X and Y. A. Find the levels of output X and Y at which profit is maximized. B. Test the second order conditions. C. What is the maximum profit? Number 2. A monopolist sells two products X and Y for which the demand functions are X equals 25 minus 0.5 px, Y equals 30 minus py, and the combined cost function is C equals x squared plus 2xy plus y squared plus 20. Find A. The profit maximizing level of output. B. The profit maximizing prices. C. The maximum profit. 3. Find A. Profit maximizing level of output. B. Prices. And C. Maximum profit when Q1 equals 520 minus P1. Q2 equals 820 minus 2P2. And C equals 0.1 Q squared plus 0.1 Q1 times Q2 plus 0.2 Q2 squared plus 325. This is the end of study session 9. Thanks for listening.